Hi, everyone. Today we're going to be showing off Vulcan, which is a chat interface to Workbench and Ansys Mechanical to help accelerate the pre-processing and FEA setup. In today's example, we're going to be using a strut mounting bracket, which has three mounting locations for struts to hold a minimally constrained body to a rocket. To get started, we upload our geometry via the geometry import in the bottom left of the Vulcan window, and then we begin to describe the situation that we are attempting to model. Via the context that you just provided and the geometry that was uploaded, Vulkan can then start to analyze what the situation is that you're trying to model and how it can help set you up. It will ask clarifying questions that are relevant to the actual setup of the simulation that you're trying to do. We then upload a spec sheet containing the actual loading conditions that we are expected to experience during the rocket launch, and that is contained in an Excel spreadsheet, which Vulkan can then parse along with the context that you provide as the engineer to help set up the simulation. Now that we've set up in Workbench, we can move on to pre-processing the geometry in ANSYS Discovery. Looking at the actual geometry, we can see that we have four bolt hole locations that mount to the actual airframe, and then three strut mount locations, which are the six tabs that extend vertically. To aid in the setup of our actual static simulation, we like to set up this part as a collection of mid-surface faces that have easily modifiable thicknesses to quickly iterate on the part. One nice aspect of Vulkan so far is that we are able to mid-surface parts that would normally be too complex to mid-surface via the automatic method in ANSYS Discovery. This can save users a tremendous amount of time, as creating the mid-surface representations would require doing so manually in Discovery or whatever CAD software that you prefer. As you can see, Vulkan can create an accurate mid-surface representation of this body in under 10 seconds, something that would manually take an engineer roughly 30 minutes to do themselves. For this part, mid-surfacing was the only pre-processing that we needed to accomplish, and now we are ready to set up in Mechanical. We can now set material properties and thickness of the actual surfaces contained within the geometry via an upload of a PDF of 7075 T6 from MatWeb's online resources. For this situation, we can leave meshing up to Vulkan, which chooses a 1 mm quad size with mid nodes enabled and stitches all of the surfaces together such that they're all connected like the original geometric body. In the original spec sheet that we uploaded, all we had were the distances of the struts, the distance from the strut ends to the center of gravity of the minimally constrained body, and the actual accelerations acting on the entire system itself. Because of that, we can have Vulkan set up and run a Python script that would calculate the actual forces in each of the struts of the minimally constrained body. And in this case, because we are only concerned about struts 1 through 3, which mount to this strut mount bracket, we solve for just those struts. We can then automatically apply the strut forces in the correct directions via the unit vectors given in the original spec sheet to each of the strut mounting locations. Next, we ask Vulkan to apply the boundary conditions, which are constraining the body via remote point connections with displacements set to 0 for each of the bolt holes. It does so automatically, setting up the 4 remote displacements at each of the bolt holes. And now we are ready to solve. Now that we have the simulation fully set up, we can ask Vulkan to run the simulation, which will run it and then automatically populate all of the results for each of the load steps. It then is going to set up and run a modal simulation for each of the different load steps seen to see how the stress in the body will affect the mode shapes. Now that our analyses are complete, because Vulcan automatically populated all of the results for us, we can very easily quickly go and see how our system performed. In this case, we can see all of our mode shapes are well outside any excitation frequencies that we would see during a launch. However, we can see that the actual part itself is under-optimized for the loading cases. We only have 130 megapascals of stress at the critical points, and we can see that that would be well under the 503 megapascals of yielding stress for 7075 T6. So we can optimize this part further. One feature that we're super excited about is Scout. Scout enables you to go back into previous simulations and apply all of the boundary conditions, meshing settings, and everything else that you've done to a new simulation with a changed geometry. To get started using Scout, you type in the name of the previous system, which is old in this case, the old static structural simulation, and new for the new static structural simulation. Scout will then autonomously go and look at the previous simulation to determine what sort of loading conditions and boundary conditions were applied to the previous geometry before any design changes. It will then, upon context and review from the user, go and apply all of the same conditions, mesh settings, everything else to the new geometry and run the exact same simulations that you did in the first place on the new geometry. This can save users on the order of 30 minutes to 2 hours of manual setup time that we hope can help accelerate your engineering workflows. Scout now runs in the background autonomously, freeing the user up to do other tasks if they so wish. Now that Scout's done, it sends a desktop notification to let the user know that it's completed the new simulation, and you can go and look at all of the stress and mode shapes of the new body that you've uploaded. Another problem that we've heard from users is spending too much time looking through textbooks, design guides, and standards to find the right equations to model a given scenario. We've created search functionality to easily parse through these internal design guides, textbooks, and standards. By providing candidates of potential equations to model designs via first principles, we are aiming to help prove out early design concepts quicker and streamline the analysis process. To ensure trust, we are providing citations linking directly to the source and the ability to export directly to users' native formats, including MATLAB, MathCAD, Excel, and Python. For this example, we are performing a bolted joint analysis of the strut mounting bracket to ensure that we will not see the bolts yield due to axial and shear forces. We also want to ensure that the bolts will not yield due to cyclic fatigue, using Shigley's to help model these equations properly. Based on the input geometry, simulation, and conversational history, our product automatically generates design slides for the user, taking the time from hours working on design slides to minutes.